Hello and welcome. This is the very end of Packet 4. I had originally intended to put this in one video, but decided to split it up into two. So what we're looking at here is the left and the right-hand derivative. Recall that the derivative is defined in terms of a limit. One way of writing it is the limit as h approaches 0 of f of a plus h minus f of a over h, where a here represents the x value that you're trying to find the derivative at. And remember that visually the derivative corresponds with the slope of the tangent line. Now this limit right here is just the regular old limit. The limit is h approaches 0. That's how we defined the derivative, was just a regular limit. But remember that a regular limit can be broken down into a left-hand limit and a right-hand limit. And for the regular limit to exist, the left and the right-hand limits both have to exist and be equal to each other. So here we're just breaking up the left-hand and the right-hand limits. So if we're looking at the left-hand limit, h is approaching 0 from the left. And when we write a plus h, that's going to put this x value that we're plugging into the function a little bit to the left of x equals a. So in this picture, the left-hand derivative, a is 0 and h is approaching 0 from the left. So we're taking 0 and we're adding a negative number to it, which moves it over a little bit to the left. And then computing the slopes of those secant lines as h shrinks to 0, as that little interval shrinks to 0. So the points, the x values that we're going to be plugging in to the function to get the slopes of our secant lines, those x values are going to be getting closer and closer to 0. So when we do that, the slopes of these the slopes of these secant lines are going to be getting closer and closer to the slope of this tangent line in the picture. You can do the same thing, but let h approach 0 from the right side, in which case h will be positive, and so a plus h is going to be a little bit bigger than a. So in this case again, a is 0, so a plus h would be 0 plus a little bit. So then our secant lines are going to be coming in this way. So let me draw the little arrow here. The secant lines are getting closer and closer to the tangent line in this way. All right, I'm not going to spend too much time on this, but I just wanted to give a general overview. So you have to have both the left-hand derivative and the right-hand derivative both existing and be equal to each other in order for the regular derivative to exist. So this idea helps us in helps us understand why the derivative won't exist in the following places. So at a corner, for example, at a corner, the left-hand derivative is going to have one slope, and the right-hand derivative will have another slope. Let me just show what the slopes are going to basically look like. So if you look at the left-hand secant lines, they're all going to be along this same line. You know, you'll have a point right here and a point right here, and that'll be a secant line. And all those secant lines are going to have this positive slope, whatever it is. Whereas over here on the right, you're going to have a point to the right, and then a point right here at the place we're trying to find the tangent line at. And then you'll get a secant line that looks like that. That's the jaggediest line I've ever drawn in my life. But the main thing is it's going to be some kind of negative slope, and they'll get closer and closer to maybe a slope of 0. We're not exactly sure if they're going to have a slope of 0 at that corner in that particular case. But the main thing is they're going to have different left-hand and right-hand derivatives. The slopes of the secant lines coming in from the left are going to be different than the slopes of the secant lines coming in from the right. All right. So at a corner, the derivative does not exist. At a cusp, the derivative also won't exist. And a cusp is a place where the curves have steeper and steeper tangent lines as you're getting closer and closer to the cusp. So eventually, you're going to have these super steep, almost vertical tangent lines coming in from both sides of the cusp. And that makes the tip of the cusp particularly sharp. So, you know, if we reached in here and we tried to touch it, yeah, oh boy, that's sharp. Whew. Gotta be really careful around cusps. All right. I need a laugh track. Oh, I need one desperately. So with a cusp, it's infinitely steep coming in from both sides, so we can just draw these really steep tangent lines coming in from both sides. And so since, you know, at the cusp there's effectively a vertical tangent line, the derivative is not existing there. That a vertical tangent line has an undefined slope, and so we would just say right there the derivative does not exist. Same kind of thing at a vertical tangent line here. So here coming in from the left, so if we're looking at a point right here where we have a vertical tangent line, coming in from the left, the slopes are going to get steeper and steeper. Coming in from the right, the slopes are getting steeper and steeper. And so here we have a vertical tangent line. And so the limits are both going to go to, the slopes of the secant lines are both going to go to infinity, coming in from both the left and the right. So the regular derivative is not going to exist. It doesn't exist as a number. It might be, you know, the limit might equal infinity, but it doesn't exist as a number. Also, if we have discontinuities, like this gap discontinuity in the example, last example here, coming in from the left and the right, we're going to have totally different slopes of the secant lines. For example, here's the slope of a sample secant line coming in from the left, and here would be one coming in from the right. They're just totally different, and they're not going to approach the same thing. So here's a couple more example slopes as you get closer to that point of tangency, or to that x value that you're approaching. So definitely, if you have a discontinuity, the derivative won't exist. All right, and this is related to the theorem that we're going to talk about and then prove, which is if f has a derivative at x equals a, then f is continuous at x equals a. So if the derivative exists, then the function is continuous. Or in other words, differentiable functions are continuous. If that's true, then the contrapositive is also true. The contrapositive is of a implies b is not a implies not b. So if you have taken a logic course at all, and you have a implies b, the contrapositive would be not b implies not a. A quick example of this is if it is raining, then it is wet outside. And as of this recording, it was raining and it was wet outside on the floor, on the ground. The contrapositive would be if the ground is not wet, then it is not raining. And that's also true. If the ground is not wet, then it's not raining. So that's the contrapositive. So in our theorem here, we would say if the function is not continuous, so if it's discontinuous at x equals a, then the function is not differentiable, does not have a derivative at x equals a. And that's what we were looking at in the last previous slide. We were looking at a place where the function was not continuous and therefore not differentiable. So let's go ahead and prove this theorem. What we can do is say, suppose the function has a derivative at x equals a, and then we're going to show that f has to be continuous at x equals a. So that's how the proof starts out. Now, if the function is differentiable, then by the limit definition, the limit as x approaches a of f of x minus f of a over x minus a is equal to L for some real number L. Now, this was one way of writing the limit definition of the derivative. The other way we wrote it was the limit as as h approaches 0 of f of x plus h minus f of x all over h. We also had another way of writing it using a's, like we saw just a moment ago. But this is another perfectly good way to write the definition of the derivative. These are the slopes of the secant lines, just written a little bit differently. And it's a more useful way of writing it for this proof. So continuing on with the proof, what we're going to do is find this limit as x approaches a of f of x minus f of a. And stepping back just a moment, if our goal is to show that the function is continuous, our goal should be to show that the limit as x approaches a of f of x is equal to f of a. This is our goal. That goal is going to disappear on the next slide. But that's our goal. We want to show that the limit as x approaches a of f of x is equal to f of a, because that's the definition of continuity at x equals a. So this limit that we're going to find right now is going to help us get there. It's a little bit of a trick, but it's going to help us get there. So we're going to find the limit as x approaches a of f of x minus f of a, which is part of this derivative limit, you might notice. And so the very next step we're going to take is multiply top and bottom by x minus a, so that we can create this limit right here, create this expression whose limit we know. Then by limit properties, the limit can quote-unquote distribute across multiplication as long as the two individual limits exist. And they do. This first limit exists. It's equal to L because the function's differentiable. This limit here we can figure out by just plugging in x equals a. So we get a minus a, which is 0. So L times 0 then is 0. Now you might be wondering, why didn't we just plug in x equals a to begin with? Then we would get f of a minus f of a, which is 0. But the problem is, if we plugged in x equals a, that would be assuming that the function is continuous. The only way we could plug in x equals a is if we know that the function is continuous. But at this point, that's what we're trying to prove. So we're trying to assume that we don't know if the function is continuous, so we can't take that step. So we had to follow something similar to these steps. Now we can try to show that the function is continuous by showing that the limit as x approaches a of f of x is eventually equal to f of a. And the way we can get there is by rewriting f of x as f of a plus f of x minus f of a. Seems like a convoluted thing to do, but remember, we know that what the limit as x approaches a of f of x minus f of a is. That's equal to 0. So what we can do is, by the limit property that says limits can distribute across addition, we'll get the limit as the limit of f of a plus the limit of f of x minus f of a. The second limit goes to 0 based on our work above, and the first limit approaches just f of a, because this is the limit of a constant, which is just going to be the constant itself. So this shows then that the function is continuous at x equals a, and that completes the proof. Thank you for watching, and we'll see you in the next video. Bye.